is a professor at Institute of Science in Tokyo, and also affiliated with RIKEN. We have been some collaborations with RIKEN, not specifically to Rio, but some of my students went there and working with his collaborators. And I don't know if you remember, Rio, my first and only visit to Japan. I want to come back again. You showed me everywhere, which,
Yeah,
you
I
know,
remember.
where to get the noodles and where to eat the Kobe beef. And we had a very good
Yes.
couple of days in Kobe and Osaka, and he showed me all around the neighborhoods and the best places to eat. So I still remember, and I want to come back and explore those places again. Well, also many years back, I remember in our reading group, we read Rio's paper on all reduce. I think you were maybe very first person to analyze this all reduce performance while back. Even it wasn't that popular to use in training, and you were just studying different configurations, how to get best out of this all reduced collective communication. So I still remember that our your paper we discussed in a reading group. So I'm very happy to host you today, and please
Oh, that
uh,
one. Yeah, yeah.
welcome our speaker. Yeah. Thank you.
I'm trying to find the photo of you in Japan.
Oh, I have some. I can probably find it.
One moment. Yeah, I'll start my. I found it. Okay,
Ah,
let
you
me.
found it. Okay.
Um, where's the? This one. Okay. Let me post it on
Yeah.
my slide. I'm gonna post it on the slide.
Ah, yes. That's nice photo. Thank
Right.
you.
Okay, so yeah, this was when DDM visited yeah, Tokyo. Not Tokyo, this was Osaka. Yes.
Osaka, yes.
Okay, so can I start? Yes?
Yes.
Okay. Okay. So I see too many things on my screen. One moment. Need
Yeah,
to get
there are
rid
too
of.
many small pictures on your on the screen.
Yes, yes. I wanted to see my whole screen. Okay. No, wait. There's one more thing I need to put away the. Okay. So today's talk will be about the scaling laws. And so there are scaling laws in HPC, and there's a more famous scaling law in AI. And I'm going to talk about the similarities and differences of these scaling laws. But before I discuss about the scaling laws, let's talk about the scales. So in the end, AI and both AI and HPC are ways to learn about the world we live in, and it has various scales, and this leads to the different scales that we need to resolve. In HPC, this is very clear because you can measure things in like meters, right? And then this goes from like the very small protons, these subatomic particles, all the way to the observable universe. And it spans maybe, like roughly 42 orders of magnitude if you look at this scale. So in HPC or scientific computing, different scales result in different physics, and they are solved with different methods like QCD, DFT, MD, phase field, finite element, volume, difference methods, and n-body simulations. And it's interesting that we sort of switch between mesh and then particle and then mesh and then particle again at these different scales because they become continuous from discrete and then again continuous again and discrete again, right? This all depends on sort of um, the sort of aggregate of the physics or this sort of meta physics that happens between these different scales. And so how we do this in HPC on the left side versus AI on the right side, it's, if it all boils down to how we actually describe the, these functions. So these are all functions. They're just made in a different way. They're combined in a different way. You can think of it this way. So in the left side, you see mesh-based discretization or particle-based discretization, which I showed in the previous slide that this, at different scales, we prefer one over the other. And how this can describe very complex phenomenon is that for a mesh, we rely on this piecewise linearity of the mesh, right? If you break down the mesh into a small enough component, we can describe this through a linear equation. Actually, this continuous differential operator becomes just a difference operation. And so something like the Navier-Stokes equation shown here, right? If you try to solve this analytically, it becomes like one of the most challenging math problems. But if you use this kind of discretization, it becomes a very simple linear algebra problem. But you require a huge amount of computation because there's a scale difference, right? I showed you the scales in the previous slide that requires very small meshes to cover very large domains, right? This is the scale separation problem. So for the problem to become simple enough to describe with a linear equation, you need to use many, many of these mesh points, right? Many large combination of these simple functions. On the bottom, we see the particle-based discretization. This also is comprised by this very simple function, right? The pairwise interaction can be described with this very simple equation. But when you combine n of these particles and their movement, or even just three particles, right? A three-body problem already doesn't have an analytical solution in general configurations. So as soon as you have many of these bodies, it becomes a very, very complex nonlinear system. And this is the unit which we use to describe these things. It's either the one on the mesh or the particle, right? But they come from very simple problems. This also, turning this into a linear algebra problem, like AX equals B, actually serves as a very clear-cut API between the scientists who are concerned about how A is constructed versus the computer scientists who focus on how to solve this linear equation on a computer. And that's basically LIMPAC, and how 𝐓𝐢𝐭𝐥𝐞 it became so famous is because of this clear-cut API and the significance of this equation to describe very general physics. And then we have on the right side the neural network. If you view it as a composite function, right, each layer is either a linear layer or some activation that, if, for example, ReLU is a piecewise linear function. So basically it's linear and mostly linear. And the softmax is not a linear function, but this is a sort of an exception. Most of the neural network is a combination or a composite of linear functions. And so it's different, right? Because the mesh and particle, these are all different ways of simplifying things. A mesh is, it's a localization kind of separation. A particle is like a pairwise separation of the physics. And in neural networks, it's a composite separation. So each of these functions can be very simple. F, G, H can be very simple functions. And that's why PyTorch is very powerful, because you can construct a combination of these very basic functions where you can actually hard code the derivative inside the PyTorch library and provide it to the user that way, the back propagation just becomes a combination of these hard-coded derivatives, which are pre-programmed, and you can just combine them like Lego pieces and construct any kind of complex forward function, and the backward or the gradient computation is almost automatic, right? So this is a very powerful tool, right? These are all very powerful um, simplifications of a very complex physics. But knowing this difference is very important when you talk about scaling these things, right? The reason why this is connected to scaling is once you describe it with these very simple things, all you need to do is just scale up. You scale the mesh, you scale the particle, number of particles, or you scale up the neural network. And then the complexity of the physics you can describe just keeps growing, right? There's no more, you can just brute force your way using these very simple abstractions. And I find this to be very powerful. And so does Rich Sutton. So he says in his bitter lesson, right? This is a very famous quote, right? The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. The ultimate reason for this is Moore's law, or rather its generalization of continued exponentially falling cost per unit of computation. So basically, Moore's law is an exponential law that has been continuing for decades. And when something exponential continues for decades, it becomes very, very powerful. And it's not a good idea to go against this trend, is what he is saying. And so I used to work on, in my previous life, I used to work in turbulence modeling. That's why I can talk about both sides of this scaling. So on the HPC side, we had a similar experience to Rich Sutton. So the traditional way we modeled turbulence was through very complex turbulence models. So DNS is the least amount of modeling, right? It's more brute force. And LES is somewhere in between. And this thing called RANS, Reynolds Average Navier-Stokes, is where you take any turbulent field and you can compute something called the Reynolds stress. um, it's analogous to a molecular viscous stress, right? So molecules can they will transport momentum. If there's a difference in the velocity, then this results in this kind of transport of momentum because something is moving slow, gets accelerated by the fluid that's next to it if it's moving fast. And this is translated through movement of molecules. But in turbulence, a similar thing happens, except the thing that's transporting the momentum is not the molecules, it's actually these turbulent eddies. So these vortex will transport the momentum in a similar way. And to find this analogy was sort of the way we modeled this highly highly nonlinear and chaotic movement of fluid. From a statistical viewpoint, we could model this. So in this sense, it's very similar to what machine learning does. It looks at something very complex, but it uses statistics to model the sort of meta behavior. And people use things like, these kind of Galilean invariance or material frame indifference to, all these mathematical techniques to come up with clever models. But in the end, people stopped using RANs because it can save you a lot of computation if you don't have a strong computer, but computers became very powerful and people could afford to do LES instead. And if you had an even more powerful computer, you could do DNS and get a much, much more accurate solution. And so people use the DNS to compute very, very large scale turbulence. This is maybe like 25 years ago. When the Earth simulator first came online, it was used to compute like a very large DNS computation of isotropic turbulence. It won the SC02 Gordon Bell Prize. And this actually has something that looks very similar to modern AI scaling laws. It has this power law that describes how the energy cascades from low wave numbers to higher wave numbers. Basically, big motion propagates, it feeds the energy into the smaller and smaller motions of fluids. And it behaves as this scaling law. So this is confirmed in experiments, the first paradigm, and also theory, right? The mathematicians can compute this. This is the second paradigm. And now with the Earth simulator, they were able to do this with computer simulation, which is the third paradigm. So to tie these three paradigms was a very interesting thing and show that they agree, right? Experiment, theory, and simulation agrees. Back in these days, it was not obvious that all of these things agreed perfectly. So this was a big thing. Um, and then now we have these AI scaling laws. You see, this is also a power law, right? And there are different variants of scaling laws. The original one by Kaplan um, was showing, the one on the top. And then now you have the chinchilla scaling law, which is the one at the bottom. You can think of this as like an optimal learning rate schedule scaling law. But on the other bottom right, I show this figure that also similar to the turbulence scaling law, the power law only exists in this kind of middle region, right? In the turbulence scaling law, the power law slope existed only in the middle. It's the same here. So people only plot the middle part of this, so it's a little bit misleading that people make this look like a straight line. On the left and right end, actually it becomes flat, right? Because you have a best guess error that you just cannot in the small data region, right? There's like random chance. If you don't have enough data, it doesn't learn anything, right? And you get the best guess error. And also, even if you had an infinite amount of data and compute, um, due to the irreducible error, right? There's always some error that always exists in either your data or there's some natural uncertainty that you just cannot measure. And so there's always an irreducible error, right? You will not get to like perfect. So we need to be aware that the scaling law only exists in this power law region, right? We are looking at a limited part of the entire scale. Okay, so just to contrast the difference between these two things, um, so the turbulence scaling law justified the Earth simulator, right? It was used to justify the huge cost of building that very expensive machine back in 2002. But now, like over 2 decades later, we are using these AI scaling laws to justify, the largest GPU mega clusters. And also, in the same way that CFD applications have many other issues besides just this ideal scaling behavior of isotropic turbulence, in the actual real world, we have near wall turbulence behaviors, very complex, also multi-phase and multi-physics, which um, makes this very ideal case not applicable in the actual case. In the same way, the scaling law looks all nice on paper, but actually this doesn't describe many things that are the reality of AI training is that the data quality and quantity really matter. Also, we have copyright issues and alignment issues, right? Like scaling laws don't solve everything. There are many other issues that we need to consider. So this is the similarities. Now, if you look at the differences, right, the turbulence scaling law was driven by scientific interest. And so it was a purely academic thing. But now the AI scaling law is driven mostly by commercial interest, as you can see from all the investment from these huge big tech companies. And then also from a scientific point of view, the HPC or turbulence scaling law was validation between the first, second, and third paradigm, right? But the data is the fourth paradigm, and in AI scaling laws, this is basically showing the asymptotic behavior of the fourth paradigm, like from a very uh, objective perspective, you see this very big difference scientifically, or the scientific significance of what these two different scaling laws are doing. And back in 2002, Moore's law was yeah, still very, very valid, but now Moore's law is almost dying, or many people say it's already dead. So there's a very big difference in how far you can scale this further. Right now, the only thing we can do is spend more money. Right? It's not spend more technology; it's more money now. So the part that involves the more money, this is very obvious when you look at this picture. Right? The the amount of compute that people are using to train these models is increasing 10x every 2 years, roughly, right? And you can even see this from the 10 years from AlexNet in 2012 to 2022 of GPT-4. During these 10 years, the spending, right, goes, yeah, it's exponential, actually. Because if you think about it, AlexNet was trained on 2 GPUs, each $500 for just 5 days. And that was considered like a very big effort back in the day. But now, if you look at GPT-4, well, this is not now, actually. This is in 2022 when GPT-4 was trained. Of course, this is speculation because they don't release these numbers, but they spent, yeah, roughly 90 days on 25,000 GPUs, and each of these GPUs was much more expensive than the ones used to train AlexNet. And so if this trend continues, right, in 2024, we're spending like $10 billion on our clusters, like Colossus. And then in 2026, right, like roughly, if we're spending like 5x more each year, right? So to do 10x every 2 years, you can get 2x from Moore's law, but the rest of the 5x you need to get from more spending. That's why instead of the scaling law, this should be called the spending law. Okay, but now there's some competition here that's uh, bringing down the cost, right? If you remember DeepSeek when it came out early this year, uh, the training cost for this was, yeah, roughly an order of magnitude lower than what people used to do, right? And the secret sort of lies in, if you look at the top that says total parameters, and if you look at the one that says active parameters, you see a huge difference between the total and active parameters. And this is because they're using a very sparse mixture of experts model. And um, when you use many, many experts, right, you can get huge model with, like a trillion total parameters, but the actual active parameters remains very small. And the active parameters is what is used to calculate the cost of training, right? If the active ones are the ones where you do the forward and backward computation. And so that directly is related to the cost. Of course, if you make your MOE, your mixture of experts model, too sparse, then the percentage of peak drops, right? Like, so one of the significance of what DeepSeek did is to use a very sparse MOE, but to retain this percentage of peak to be so high. What was the key, right? If you tried to do this on your own and do such a very sparse MOE with like expert parallelism, you will not get this percentage of peak. It would be much, much lower. That's why people didn't do this kind of very, very sparse MOE. But this is a HPC issue, right? Like they made, they went very low level into, like the instructions to overlap the, intra and internode, with the communication with the computation, and they even specified which SM to be used for the communication versus the computation, and very, very, very low level optimization to actually get this percentage of peak. So there are this kind of efforts to improve the implementation, but also there is a lot of improvement on the algorithm side in both HPC and AI. So when people say like scaling law, it makes it sound like they just, don't change anything and just use more compute. But that's not what's happening here, right? If you look on the HPC side, um, of course, we're interested in things to be scalable, but we are also interested in things being efficient, right? And if you look at Moore's law plotted against algorithmic gain coming from, like Gaussian elimination, going to Gauss-Seidel, SOR, conjugate gradient, and then full multigrid, that spans the same order of magnitude in algorithmic improvement. Um, and if you plot it against the number of years where Moore's law kept improving, it's roughly the same magnitude of improvement, right? And so, like my colleague once said, I quote 𝐓𝐢𝐭𝐥𝐞, he said, with great computational power comes great algorithmic responsibility. And I think this is very true. If you're using more computation, resources, and I want to say this in particular to the people doing training huge models, you have a much greater responsibility to make the algorithm much more efficient because the difference will be multiplied that much. And so I'm not saying the AI people are not improving the algorithm. If you look at the inference cost to achieve the same performance on the math benchmark, this has improved 600x from 2022 to 2024, right? So going from like Minerva 540B to Gemini 1.5 Flash, right? Now these are very old models, but now it's much even better than this, right? So, but it's roughly this kind of same order of improvement that you get from using better algorithms. And so, yeah, there's much more to be gained through algorithmic progress. And one of these keys is this thing that Leopold Aschenbrenner calls unhobbling. And now this thing is called test time compute or test time scaling law, but at the time it was called unhobbling of these models, which means extracting its true potential, right? These huge pre-trained models had a huge potential, and people knew they had huge potential at the time, but they were being hobbled by how you were doing the inference. And with more reinforcement learning, now we know how to do this, right? Now people do a lot of this kind of reinforcement learning to do test time or thinking models, right? This was proposed before people were using these kind of thinking models. But now we know what this looks like, right? Now this it's very common to use thinking mode when we use AI, right? And thinking is very effective when you want to solve hard problems like competition math, competition code, or PhD level science questions, right? These make a huge difference if you can spend some time to think about the problem, right? And so even, like geniuses like Terence Tao, when he first saw what GPT-01, this is one of the first reasoning models that OpenAI released. When he played with it, he thought it was pretty good, and but still struggling with the most advanced research mathematical tasks. Now it's gotten much better, right? With GPT 5.2, it can solve very complex math problems. And now the IQ test before O1 was the only one that went above the 100 IQ level, but now we have so many, right? Look, all of these models are above 100, which means that it's smarter than most humans, right? Like these are for this kind of IQ test, not like general tasks, but for these tests, it's very good. And then, so what are the implications of these test time scaling laws? So we need more difficult benchmarks, right? Because all the benchmarks that people keep proposing, they get conquered in like 6 months, basically, right? Like every or maybe 1 year, right? Like every year, a new benchmark comes out, and in the beginning, they can only get like 10% or even less. But then in 1 year, it goes above 90. This keeps happening. So so what is the next challenging task, right? And also, this kind of test time scaling or reasoning model is very important when you want to do AI in the science domain, right? Like if you have very good mathematical skills, or if the AI has good mathematical skills, it can do so much more. Some caveats are that this will not make the model learn something it already doesn't know, right? This is test time scaling. It's not actually training, right? This is test time. It's inference, right? So, what people call like in context learning, this is not actually updating the weights. So the model is not actually learning in the traditional sense. And so you need to have a strong base model for the chain of thoughts to lead anywhere, right? If you're a fruit fly and you think for 1 year, you're not going to solve a very difficult problem. So we need a strong base model. And the real question now that people are trying to ask is like, how strong does the base model need to be in what area for the model to get like reasoning capabilities, right? Once it can reason about which site to search for or which database to search for, the knowledge can be external. What it needs is the reasoning capability to make this decision. So what is the minimum model size to do this, right? So this is a very interesting question that's unanswered, and that could lead to the next dimension of scaling, actually. So test time scaling requires exponential cost for inference, so it's not good for customers. So you shouldn't be fooled by AI companies telling you that test time scaling is all you need, because that means you need to be the one that's paying all the money. So we need to come up with a much more clever way to do this. But for the time being, it seems like, increasing the thinking budget solves many issues. Also, people are pivoting more towards agentic orchestration of agents, right? Because one of the problems with the current sort of um, transformer-based autoregressive models is that after a certain context length, or if you go back and forth and have a conversation that's too long, the output starts to deteriorate. You may have noticed this. If you talk to it for too long, it's not good, right? So this sort of finite context window is really the weakness. And agents are good because each agent doesn't need to handle very long context, right? It can handle only one part of the problem, which is finite context length. And then you can have a million agents, and in total, it can handle many, many, many tokens, right? So it's sort of a way to go around this finite context length problem. Okay, and then so I'm gonna pivot my talk a little bit towards more HPC things. So um, uh, so we talked about a lot of the scaling laws in HPC and AI, but now the hardware what we use for AI is also changing, right? They're becoming more specialized. A typical example is the tensor cores, right? It has, um, it's very efficient for doing matrix multiplications. in low precision, right? But not all HPC, well, very few HPC applications can directly use this or benefit from this. So we need to recover the precision and maybe reformulate our algorithms to be more friendly to the tensor cores. Okay, so, but we somehow want to benefit from this sort of AI for AI cycle, which will just keep accelerating, right? The frontier AI companies are this red part. They're developing AI for AI, and this is just going to keep accelerating. Now, AI for science is like these things that spin off from this wheel. And the closer you are to this, I think the more energy you can draw. And so, yeah, this is sort of what we want. And the AI hardware will also evolve for AI. And if you want it to do AI for science, you need to somehow deal with this hardware architecture and extract its potential. So the thing we've been doing in this regard is, so we had one paper that recovered SGEM, like single precision matrix-matrix multiplication, from FP16 tensor cores. And then we did another paper which recovers double precision GEM from int8 tensor cores. So using even lower precision tensor cores to do even higher precision um, emulation, right? And these things use very different algorithms. Um, so yeah, the one that does SGEM emulation using FP16, it just uses two matrices and compensated summation. So this is, you can think of this as Kahan summation in the traditional sense. And we had to do a little bit tweaking of the rounding. Because it was rounding to zero inside the tensor cores, and you need to round to the nearest instead of rounding to zero. So we did the rounding or the accumulation outside of the tensor cores for this. And then for the int8 to FP64 emulation, we used something called the Ozaki scheme. And this one uses many, many more, not two, but 9, 11, or 13 shown in this picture, matrices to express just one double precision matrix. And then if you want to multiply two of those things, it results in many, many more computations. But since the tensor core is so fast, it does make sense to do this in many cases. Also, there are efforts to do like stencil or sparse matrix multiplication, FFT, and multi-grid on tensor cores, right? But so in general, right, if your problem is not compute bound, tensor cores will not help, okay? So there are many publications on using these other things, but if you are bound by the memory bandwidth, if you're limited by the memory bandwidth, then the tensor core does not enhance the memory bandwidth, right? If you're limited by the memory bandwidth, you just can't get the data into the tensor cores fast enough. And so even if the tensor core is infinitely fast, your computation will not accelerate, right? That's a very basic thing. So you need to change the algorithm. So there's some precedence of this. What I'm showing here is some examples of this. So I mentioned this isotropic turbulence thing that was computed on the Earth simulator. And roughly at the same time of Earth simulator, there was GRAPE-6. And there was this whole line of ASICs called GRAPE and MD GRAPE for molecular dynamics. These are the same series of GRAPE machines. I worked on the third generation of MD Grape at the time, and MD Grape 3 was actually, the whole machine. A cluster of MD Grape 3 was created, and this was equivalent in terms of flops. It was equivalent to the aggregate, the sum of all 500 supercomputers at the time, right? It's much faster than the top one, except it's not on the top 500 list because it can't do LIMPAC, right? It can only do n-body because it's an ASIC for n-body. So the hardware is saying, I want n-body, right? But what I was trying to do at the time was this kind of spectral DNS, which wanted to do FFT. So it's like the very opposite thing that n-body wants to do. So I changed the method, right? Like if you are willing to completely change the underlying method, you can turn this turbulence simulation into an n-body problem and utilize this extremely fast hardware. So that was sort of the work I was doing during my PhD. And now I'm doing the opposite thing. I'm taking an n-body problem. I'm working with the GROMACS people. And I'm, instead of using particle mesh Ewald, PME, which is based on FFT, I am turning this into, well, this is an n-body problem, right? So I'm using this thing called the fast multiple method, which is a order n-body solver. And I'm trying to run this on tensor cores. And you can actually do this. It turns out that the translation operators called the M2L translation it's a matrix vector multiplication, but you can actually reconfigure this so that it becomes a matrix multiplication. And then it runs very fast on tensor cores. And since the fast multiple approximates this kind of far field interaction, low precision is tolerable. So this is now trying to change the algorithm, right? Not just trying to use tensor cores as is for a sparse problem or an n-body problem. I'm trying to actually change it into a matrix multiplication. I'm making this effort so that the tensor core can be utilized. And I'm sure there are many other examples because the scientific applications are flexible. Hardware is much less flexible. And with AI driving the field, we actually have no say in the design of the hardware in most cases, right? There are some special cases where there was some co-design, but in the majority of cases, it's best to change something on your side than to ask, Jensen to change it on his side. Okay, so coming back to this picture because I really like this kind of view, that these simple abstractions, right? They're very powerful in the sense that once you have this, you can just brute force your way. In most cases, anything beyond this, if Moore's law keeps continuing, and I'm not sure it will in the future, but if people keep spending more money as they do in the AI field, something like it will keep continuing, right? We will continue to have more compute. And so we can brute force more of these things, but you need to have this kind of a basic, very simplified abstraction that can eventually describe very complex physics if combined in different ways, right? So scaling is not just about using more and more compute. It's more about designing this simple abstraction that is scalable, right? When you think about your algorithm, is it scalable, right? If you're think about a new idea in either HPC or AI, you need to always think at large scale, the advantages still hold? And I think this is a very important thing to think both in HPC and AI. Okay, finally, I'd like to thank all my collaborators from all these different institutions that helped me give you this presentation. So I think I'm on time, right? Thank you.
Yeah, thank you. Maybe we can get questions now.